Hello there, and welcome to Science for Sleep. I'm glad you've arrived. Maybe you're listening from a quiet room, lights low, blanket pulled just right. Or maybe it's earlier in the evening, and you've found a still moment in a busy day. Wherever you are, this is your space now. A space made for calm, for curiosity, and for drifting softly into questions that don't need quick answers. Tonight, we're going to explore something strange. Not a monster in the dark, not a distant star exactly, but a limit, a boundary. One of the most famous lines in the entire universe, the speed of light. But more importantly, the idea that maybe, just maybe, something moves even faster. Not in a loud or obvious way, not in a flash, but faster in a way we don't quite see. That's the question tonight. Is there a speed faster than light we just can't see? It's not the kind of question you shout. It's not the kind you race to answer. It's more like a pebble dropped gently into a pond. The ripples take a while. You can't see all of them. Some are so faint they pass under the surface, where things are quieter. That's what we're doing here. Letting the ripples reach us. Letting the question take its time. And if this kind of gentle wandering feels good to you, if this space, this softness, is something you'd like to return to, I'd be grateful if you gave the video a like or subscribed for more. It helps keep this corner of quiet curiosity going. And if you're listening from somewhere special, the countryside maybe, or a city window with the blinds pulled just enough to see the moon, tell me about it in the comments. I love to imagine where these stories are being heard. A quiet chair in a quiet room, a bunk bed with a sleepy sibling below, a tent under the trees. Wherever you are, it's part of the map now. A soft little dot of light on the edge of the night. So, here we go. We're going to start where the story usually begins. Light. You know what it is. You see by it. You live by it. Maybe right now, there's only a little bit in the room with you. Just enough to make out the shape of the walls or the edge of your pillow. Maybe just your screen. But light, in its most basic form, isn't only brightness, it's motion. It moves, and it moves fast. In fact, nothing, as far as we know, moves faster. Light travels at about 299, 792, 458 meters per second. That's roughly 300,000 kilometers per second, or around 186,000 miles per second. Numbers so large they start to feel like nonsense, unless you compare them to something. A beam of light could go around Earth more than 7 times in 1 second. The light from the sun takes about 8 minutes to reach us, even though it's 93 million miles away. If you shined a flashlight at the moon, the beam would hit its surface in a little over a second. That's what we mean when we say speed of light. It's not just fast, it's a kind of ultimate, a top speed, a limit that isn't just hard to break, it's supposedly impossible. But where does that idea come from? To understand it, we go back to Einstein. The theory of special relativity, published in 1905, made a startling claim. The speed of light is always the same, no matter who is measuring it, and no matter how fast they're moving. That sounds strange, but it was a huge turning point. Before Einstein, it was assumed that, like everything else, light's speed might be relative, that it might change depending on how fast the observer was moving. Like when you're in a car and another car passes by, its speed seems different depending on whether you're moving too. But light doesn't behave like that. No matter what, if you measure it, you'll always get the same number, even if you're running toward the light source, even if you're flying away from it. That number, around 300,000 kilometers per second, doesn't budge. And because of that, everything else has to adjust. Time, space, mass. All of them bend and flex in response to this one unshakable rule. Because the speed of a light must stay the same. It's why time slows down the faster you move. It's why distances shrink at near-light speeds. And it's why, as far as we currently understand, nothing with mass can ever reach or exceed the speed of light. Because to do so would require infinite energy, infinite mass, infinite time, and we don't have those things. not in any practical sense. But here's where it gets interesting. If light is the fastest thing in the universe, then why do so many parts of the universe seem to outpace it? You see, in some ways, the idea of the fastest thing is more complicated than it sounds, because speed depends on what you're measuring, and how. Take the expansion of the universe. You've probably heard that the universe is expanding, not like an explosion, but like a balloon slowly inflating. Galaxies aren't flying outward through space. Space itself is stretching, carrying the galaxies with it. And here's the strange part. Some galaxies are moving away from us faster than light. Does that break the rules? Not exactly, because the rule says nothing can move through space faster than light. But if space itself is stretching, then the distance between objects can grow faster than light could ever travel. Nothing is violating the speed limit. The road itself is just getting longer between each step. But it raises a question. If space can stretch faster than light, could other things go faster too? Could there be something that just slips past light's barrier, not by cheating, but by living in a different lane? There's a word for this kind of thing, a name that comes up in theoretical physics when people imagine faster-than-light particles. The word is tachyon. A tachyon, if it exists, would always move faster than light. It couldn't slow down to light speed, just as nothing else can speed up to it. It would be permanently locked on the other side of the barrier, unreachable, invisible in most ways. There's no evidence tachyons are real. They come out of certain mathematical models, but we haven't found one. They might just be a placeholder for ideas we don't fully grasp yet. But they're one way of asking the deeper question. Is the speed of light really the final limit? Or is it just the fastest thing we can see? And if there was something faster, how would we know? That's the tricky part. Light is how we see. Light is how we measure. Even telescopes, even particle detectors are using some form of light. Visible, infrared, X-ray, gamma. All of our observations rely on signals that move at or below that speed. If something moved faster, we wouldn't catch it. We wouldn't track it. We might not even notice it pass by. Because the tools we use are built on light's timing. They can't beat it. They follow behind. It's like trying to hear a whisper that arrives before sound exists. But maybe there are other ways to look. Not with our eyes. Not with our usual tools. Maybe through indirect clues. Through math. Through the behavior of particles. Through patterns that don't quite add up unless something faster was involved. Or maybe the universe has already hidden those things beyond our reach entirely. Not because they're forbidden, but because they're irrelevant to the way we experience time and space, like a shortcut through another dimension, visible only from outside the map. That's where some ideas in physics start to pull at the edges, things like extra dimensions, hidden variables, ideas that are hard to picture, but might help explain why the universe behaves the way it does, why certain events seem connected instantly across vast distances, why entangled particles act in harmony even when separated by light years. Quantum entanglement, for example, doesn't let us send messages faster than light. But it does raise questions about how information can travel, or appear to, without any delay. Einstein called it spooky action at distance, and even now we don't entirely understand it. Maybe that's the key. Not to break the speed of light, but to shift the question. Instead of asking whether something can move faster, maybe we ask whether there's a different kind of motion altogether, a different kind of connection, something that doesn't race across space but skips the need for travel entirely. That's not science fiction. It's not teleportation or time machines. It's just acknowledging that our definitions of speed, of distance, of cause and effect might be local. They might apply to our layer of the universe, but not to all of it. And that's worth sitting with. Not rushing, not trying to solve, just letting the idea settle. That light, for all its speed, might not be the last word. That there could be a deeper structure we haven't touched yet. Not because we're missing something obvious, but because we're using the only senses we have. Right now, wherever you are, in bed, in a chair, on a walk in the dark, light is already on its way to you from stars so far you'll never see them. photons are crossing the void, quietly, persistently. They're not late. They're right on time. But maybe there's something else that doesn't take that long. Something that was here before the light even left. Maybe not, but maybe. Let's stay with that thought as we go further. When we say that light is the fastest thing we know, we're not exaggerating. There's no special case where something beats it, no tiny particle we've seen outrun it, no spaceship, no blast of energy, no shortcut through a star. In the world we can measure, light moves at the top limit. It's not just fast, it's the ruler against which everything else is measured. But what does that actually mean? Most of the time, when we think of speed, we're thinking about distance over time. How far something travels and how long it takes. A car going 60 miles an hour, a plane covering thousands in a few hours, a fast pitch in a baseball game. Speed is relative. It depends on who's moving and who's watching, but light doesn't work like that. If you were standing still and watching a beam of light pass by, you'd see it travelling at around 300,000 kilometers per second. That's the number most of us learn. It's massive. It's almost unthinkably fast. But here's the strange part. If you were somehow able to jump on a spaceship and travel at half the speed of light, an impossible feat, but let's pretend, and that beam of light passed you, it would still be moving away at the same exact speed, 300,000 kilometers per second. It doesn't matter how fast you're going. The light doesn't change its speed to match you. It doesn't slow down or speed up from your point of view. It always travels at the same rate. This fact is so consistent, so reliable, that it actually forces time and space themselves to bend around it. Einstein realized this over 100 years ago, and it turned our understanding of the universe upside down. It meant that time isn't fixed, that the faster you move, the slower your own time ticks. It meant that distances themselves shrink when you approach the speed of light. That simultaneity, two things happening at the same time, isn't as simple as it seems. All of this comes from one truth. Light speed doesn't change. It's not negotiable. It doesn't care about your direction, your speed, or your reference frame. It just is. And so, in many ways, light defines what's possible. It sets the border between what can happen and what can't. It's the outer wall of the speed universe. That might not seem important when you're walking down the street or watching the sky. You never notice it directly. It doesn't affect your groceries or your evening plans. But it's there, underneath everything, shaping how events unfold. The limits of motion, the rhythm of time. The most interesting part is that light isn't just fast. It's the thing that shows us everything else. We don't see objects instantly. When you look at a distant star, you're seeing it as it was, not as it is. The light from that star may have taken 10, or 100, or 1,000 years to reach you. Some of the stars you can see tonight might not even be there anymore. They might have burned out centuries ago, but their light hasn't finished arriving yet. In that sense, the speed of light isn't just a limit, it's a delay. It's the reason we're always looking backward, never quite in sync with the present of the universe. You could say we live in the past without realizing it. Every time we look into the sky, we're time travelers in a very literal sense. That's the beauty and the strangeness of it. Light shows us the universe, but it doesn't deliver the present. It gives us history, luminous, beautiful, delayed. Even here on Earth, light takes time. From one side of the planet to the other, it takes a fraction of a second. When you have a video call with someone halfway around the world, part of that delay, tiny as it is just light taking time to arrive. This isn't because light is slow, it's because distances are vast, space is wide, and even the fastest thing we know takes time to cross it. But the question remains, is it truly the fastest, or just the fastest we can observe? Before we chase that further, it's worth asking what light actually is. Not in the poetic sense, but physically. Light is made of photons. These are quantum particles, tiny packets of energy that also behave like waves. You might have heard the phrase wave-particle duality. It just means that in the quantum world, things don't behave the way we expect. Light is both a stream of particles and a set of oscillating waves. Not one or the other, but both, or neither, depending on how you look at it. What's important here is that photons have no mass. None. They're not heavy. They don't rest. And that turns out to be essential. Because in physics, anything that has no mass must travel at light speed. There's no other option. It's not that they choose to go that fast. It's that they can't go any slower. It's kind of like a rule of existence. No mass. Then you're moving at the speed of light. Always. That's why nothing with mass, like protons, electrons, planets, you, can ever reach that speed. Because it would take infinite energy to accelerate something with mass to light speed. You'd get heavier and heavier as you got faster, requiring more and more energy for smaller and smaller gains, and as you approach the limit, the numbers explode. It becomes impossible. So for us, the speed of light is a wall. We can get close, in theory, but we can't break through. That's why science fiction often turns to wormholes or warp drives when it wants to imagine faster than light travel, because as far as standard physics goes, the speed of light is the end of the road. But you might wonder, if light moves that fast, why don't we feel it? Why doesn't it blow past us like wind? The answer is that light doesn't interact with us that way. It carries energy. Yes, it can warm your skin. It can power photosynthesis. It can push tiny particles in space, something called radiation pressure. But it's not a wind in the way we feel air. It passes through vacuum. It needs no medium. It doesn't require air or particles to move. It moves because it has to, because that's what light does, and because it travels in straight lines, at least unless it hits gravity. It moves with perfect quiet. There's no rush to it. No turbulence. It's the fastest thing we know, but it doesn't act like it. It's also one of the oldest things in the universe. The cosmic microwave background, the leftover radiation from the Big Bang, is light that's been travelling for nearly 14 billion years. It's not visible to the eye anymore. It's been stretched and cooled by time, but it's still here, still moving, still lighting up the story of the universe's beginning. So when we say light is fast, we're not just talking about speed. We're talking about reach, about time, about memory. It's the thread that connects the now to the then. The only reason we know what's out there is because light brings us news. News from long ago. News that may already be outdated, but news all the same. And yet, as fast as it is, it might not be alone. Because when we talk about speed, we usually mean travel, a journey, point A to point B. But what if something doesn't travel? What if it connects instantly? Quantum physics offers some strange clues. Quantum entanglement, which we'll spend more time with soon, suggests that two particles can influence each other no matter how far apart they are. No delay, no signal, just immediate correlation. Now, most physicists agree that this doesn't mean information travels faster than light. But it still raises questions about what travel even means in the quantum world, about whether light speed is the limit of motion, or just the limit of one kind of interaction. We'll come back to that. Because before we can ask whether anything is faster than light, we need to sit with what light really is, why it's always that speed, why it doesn't change, and whether that speed is a fundamental part of reality, or just a feature of the surface. If that speed is constant, maybe it's built into the structure of the universe itself, into the geometry of space and time. That's what Einstein showed. That space and time are not separate things, but one continuous fabric, spacetime. And the speed of light isn't just a limit, it's a property of that fabric, like the tension in a rope or the slope of a hill. It's not just a number, it's the shape of reality. Which means if we ever find something that truly exceeds that speed, not in theory but in fact, we'll be looking at something deeper than we've ever touched, but we're not there yet. For now, we sit with the light, not just as something we see, but as the messenger, the guide, the fastest thing we know. There's something almost strange about the idea that light, of all things, has a limit. You'd think, if anything in the universe was truly free, it would be light. It doesn't weigh anything. It doesn't need fuel. It moves without being pushed. It carries energy, yes, but it doesn't carry mass. No friction, no resistance, just motion, always. And yet it stops at a particular number. It doesn't go faster, not even a little. Always the same, always that roughly 300,000 kilometers per second. That's not just a number we measure. It's a number we see again and again in the way everything works. But why? Why can't light go faster? To understand that, we have to step out of what feels familiar. We're used to thinking of speed as something you can always increase. Press the pedal harder, add more energy, push a little longer, and that's true for a lot of things. But it stops being true when you get close to the speed of light. Because the faster you go, the more energy it takes to keep accelerating. And the more energy you put in, the heavier, more massive the object becomes. That's not just poetic language, that's physics. In relativity, energy and mass are tied together. The more energy something has, the more mass it effectively carries. So as you go faster and faster, you're not just increasing your speed, you're increasing how hard it becomes to keep going. You're dragging more weight with every step. And as you approach the speed of light, that weight doesn't grow gradually. It skyrockets. It explodes. The amount of energy you'd need becomes infinite. And infinite isn't just a big number. It's a physical impossibility. There's no fuel tank that big. No engine strong enough. Not in theory, and certainly not in the real world. But light isn't trying to reach that speed. It's not building up to it. It simply exists at that speed. Always. That's because photons, the particles of light, have no rest mass. None at all. Which means they're not accelerating up to light speed. They're born there. Every photon that's ever existed has always moved at the same speed. Not faster, not slower. That's just what it does. It's not aiming for it. It's not working toward it. It just is. You can't slow a photon down to a stop. You can't trap it in place. You can absorb it, reflect it, bend its path. But you can't get it to stay still. It doesn't have a state of rest. Its natural state is motion. And its motion always is that same speed. That gives light a kind of reliability that's hard to match. No matter where you are in the universe, no matter what direction you're looking, no matter how fast you're moving, light always arrives at the same pace. That's not just useful for measuring distance, it's essential for how physics works. Because that constant speed gives us a reference point. A standard that doesn't shift depending on your perspective. Without that, time wouldn't behave consistently. Events would blur. Cause and effect would become slippery. But because light speed is constant, we have a kind of framework, a structure. It's not arbitrary, it's built in, and that's why it becomes the limit. Not because something is blocking faster speeds, not because there's a law that says stop here, but because the way the universe is stitched together makes that speed the outer edge of what's possible. It's like the maximum pitch a violin string can make before it breaks, or the fastest a wheel can spin before the tyres fly off. Not a punishment, not a refusal, just a physical result of the properties involved. And when you realise that, you also start to understand why so much bends around that number. Time stretches as you get close to it. Space contracts. Mass grows. Not just for light, but for anything approaching that threshold. The equations of relativity aren't about what light wants to do. They're about what happens to everything else that tries to chase it. But light doesn't notice. It doesn't feel like it's moving. From the photon's own point of view, if it had one, no time passes between when it's created and when it's absorbed. The journey is instantaneous. It doesn't experience space the way we do. It's not flying through a hallway. It's simply moving at the only speed it knows. That's one of the deeper paradoxes. For us, light travels. It moves through space. It takes time to arrive. But from the light's perspective, if we could imagine it, there's no distance, no time, no during, just a beginning and an end. It's only because we exist at sublight speeds, because we're massive, slow-moving beings, that we experience the space in between, that we see light as something crossing a gap, and in a way, that highlights just how limited our perspective really is. We live in a world that's defined by delays. Sound takes time to travel. Light takes time to reach our eyes. Even our thoughts, carried by electrochemical signals, are not instant. They move fast, but not infinitely fast. Every sense we have is lagging slightly behind the present. Every observation is a glimpse of something that already happened. So the speed of light becomes more than a number. It becomes the edge of perception. If anything were to go faster than light, we wouldn't see it. We wouldn't hear it. We might not even be able to detect its presence unless it left some kind of footprint behind, something indirect, a trail. And that's one of the reasons why physicists take this limit so seriously. Because it's not just a question of how fast things move, it's a question of what's knowable, what's observable, what's part of our reality. Now and then, theories come along that imagine ways around it. Wormholes, warp drives, particles that only exist at superluminal speeds, and we'll get to those. But even those ideas don't necessarily break the limit. They go around it. They find loopholes. They don't say, let's go faster. They say, let's change the map. Because that limit, that speed, is baked into everything we understand. Even the way we define a meter depends on the speed of light. Since 1983, the official definition of a meter is the distance light travels in a vacuum in 1/299,792,400th of a second. We don't measure light against space. We measure space against light. That's how central it is. If the speed of light weren't constant, our entire system of measurement would fall apart. Clocks, GPS, even the timing of satellites relies on that consistency. A tiny change would ripple through technology, through engineering, through science. So when we say light has a limit, we're not saying it's flawed. We're saying it's foundational. It's the ceiling and the scaffolding at once. Which leads to another quiet realization. If the universe has a speed limit, then it also has boundaries on interaction, on influence. You can't push something instantly across a distance. You can't affect a faraway star the moment you think about it. Even gravity, which feels instant here on Earth, travels at the speed of light. So when two black holes orbit each other and eventually collide, the gravitational waves from that event don't reach us instantly. They travel. They move at light speed, and we feel them long after they've begun. That delay is part of the design. And that delay is also the reason why, in a universe so large, there's so much we'll never know in real time. So many events still on their way. So many moments we've missed or will never catch up to. Light is doing its best to keep us informed. But even it can only do so much. It's a humbling thought, but also a beautiful one. Because every photon that reaches you, every speck of light in your eye, has crossed space to find you, has taken the journey, has obeyed the limit, has travelled without stopping, without slowing, just to deliver a message. Not a message in words, not even a message in meaning, just presence, just proof that something happened, far away, long ago, and that you are part of the receiving end. So when you ask why light has a limit, maybe the answer is this. Because the universe needs a boundary between the now and the not yet, between what we can affect and what we can only witness, between what's part of our story and what's still on the way. It's not a failure, it's a rhythm, the timing of everything, and maybe, just maybe, there's something beyond that rhythm, a beat we haven't heard, a motion that doesn't follow the same rules. If it's out there, we haven't caught it yet, but we're listening. When you think about speed, it sounds like a simple idea. How far something goes and how long it takes to get there. That's the definition we're taught early on. Distance divided by time. A car covers 60 miles in an hour, so it's moving at 60 miles per hour. A runner finishes 100 meters in 10 seconds, so they're at 10 meters per second. It's straightforward. But that simplicity is an illusion. When you look closely, speed is less about movement and more about relationships. The relationship between space and time, and the way we compare one frame of motion to another. The first question is, speed relative to what? Nothing is moving in absolute terms. When you say a car is going 60 miles per hour, it's relative to the ground beneath it. But that ground is spinning with the Earth, and the Earth is orbiting the Sun at about 30 kilometers per second. The Sun itself is moving through the Milky Way. Our entire galaxy is drifting through space. So what's the car's true speed? There isn't one. It depends on which reference point you choose, and that's where speed gets strange. Because when you zoom out, there's no fixed frame of reference. Nothing in the universe is truly still. Everything is moving relative to something else. The only exception, as far as we can tell, is the speed of light. It's constant no matter where you are, no matter how you're moving, and no matter what you measure it against. But for everything else, speed is always a matter of perspective. You can only talk about motion compared to something else that's assumed to be stationary, even if that stationary thing is also moving in some larger context. It's a nested illusion, one layer inside another. So what does that mean for light, and for us? When we ask what speed really is, at its core, speed is just change of position over time. The tricky part is that both position and time are not as solid as we imagine. We treat space as though it's fixed, like a grid we can map. We treat time as though it ticks the same way everywhere, like an invisible clock that never changes its beat. But relativity shows that neither is true. Space can curve, time can stretch. They're not rigid, they're not absolute. They're part of the same fabric and they flex depending on gravity, energy and motion. This means speed isn't just about moving through space, it's about moving through space-time, a single continuum, and in that continuum light is the defining feature. Light sets the maximum slope for any path you can take. If you think of space-time as a kind of surface, then light's speed is the steepest line that anything can follow. Nothing with mass can tilt its trajectory to be steeper than that. It's a built-in geometry. When you start looking at speed this way, it stops being just a number. It becomes a question of how things interact with space-time itself. When a particle moves, it's not just sliding across a fixed background. The background is part of the movement, and that's why the speed of light shows up in equations everywhere, not just in physics about light, but in anything that deals with cause and effect. If something could move faster than light, it would break causality. That is, the chain of events, cause leading to effect, would get scrambled. You could see the effect before the cause. A signal could arrive before it's sent. It sounds impossible, but that's not just because we can't imagine it. It's because, in the structure of space-time, faster than light travel would literally tilt time backward. The sequence of events would no longer make sense, and the universe, as far as we can tell, doesn't allow that. But let's step away from the big physics picture for a moment. On a more intuitive level, speed is also about perception. We experience speed not just as a measurement, but as a feeling. When something passes us quickly, we sense the motion because of how our eyes and ears detect changes. We watch the blur. We hear the shift in sound. Like when a car races past and the pitch drops, that's the Doppler effect. Our brain interprets those signals as movement through space and time. Yet, our perception of speed is incredibly limited. For example, when a planet orbits the Sun, we don't feel the motion at all. The Earth is moving at roughly 67,000 miles per hour around the Sun, and the Sun itself is moving around the galaxy at hundreds of thousands of miles per hour. But we experience none of it. To us, it feels like stillness. Speed, in that sense, is invisible unless we have something to compare it to. This invisibility of motion makes the question of faster-than-light phenomena even trickier. How would we even recognize it? If something moves faster than light, the signals we rely on to perceive motion would arrive after the fact. We might see an effect without ever seeing the thing that caused it. It's like trying to watch lightning when the flash never reaches you. You only hear the thunder long after whatever happened is over. In the quantum world, this is even stranger. Particles don't have well-defined positions or speeds until we measure them. They exist in probabilities, in a haze of possibilities. When we measure them, we force them to take on a definite state. But in between, speed becomes almost meaningless. A particle's motion isn't the same as a baseball flying through the air. It's more like a set of potential paths that only resolve when we look. So what makes speed, speed? It's partly the interaction between space and time, partly the way we measure and define change, and partly it's just a reflection of the limits of our perception. There's another angle here too. Speed isn't only about how fast something moves through space. It can also be about how fast information moves, and that's what makes the speed of light so important. It's not just the speed of photons, it's the speed of causality itself, the fastest that any signal, any influence can travel. When you push something, the information about that push, the force, doesn't travel instantly through the object. It moves at the speed of sound through the material. In metal, that's faster than in wood. In light, it's instant across the photon itself. But the speed of light defines the ultimate cap on how fast any information, any signal, any cause can ripple through spacetime. If something could carry information faster than light, it would be like bypassing the universe's own conversation rules. You'd get the answer before the question is asked, and we have no evidence of that ever happening. The experiments we've done, even with quantum entanglement, all agree that information still respects the light speed barrier, even if the correlations between particles appear instant. Still, the question lingers. Could there be some other kind of speed that doesn't follow this rule? Maybe not in the sense of movement, but in the sense of connection. Something that doesn't have to travel across space because it's already everywhere. Some physicists have speculated about this with concepts like the quantum field, or the idea that space-time itself might emerge from something deeper, something beyond distance and duration. For now, speed as we understand it remains grounded in light's example. Every other kind of motion we know, from a drifting leaf to a distant spacecraft, is measured against that ultimate benchmark. And yet, when you think about it, speed is only half the story. The other half is time. Without time, there's no way to define speed at all, no way to say something is fast or slow. It's all tied to how we measure moments passing and how we compare one moment to another. So maybe the better question is, how does time itself behave when we get close to these limits? If speed is about distance over time, and time changes when you move, then the meaning of speed shifts too. It stops being just a number and becomes a question of experience. Sometimes the fastest things are the ones we don't even notice. They pass through, leave no mark, move without sound or weight. A breeze that barely lifts a curtain, a shadow that shifts without anyone watching. You don't feel them arrive, and by the time you realise they've moved, they're already gone. There's something important about that, about motion that doesn't draw attention to itself. Because not all speed is loud, not everything fast has to be forceful. Some of it is quiet, subtle. It's easy to forget that speed doesn't always mean intensity. Light, for example, doesn't make noise when it moves. It doesn't disturb the air like sound does. You don't hear it rushing in. It simply arrives. It fills the space between things. Even when it travels millions of light years, it does so without breaking anything. No crack, no spark, just steady movement through vacuum, as smooth as anything can be. And shadows, well, they aren't things at all, they're just the absence of light, a byproduct. They seem to move, but they're not moving in the traditional sense. They're the result of other things moving, objects, light sources, and they stretch and drift in response. But here's a strange thought. Shadows can, in a sense, move faster than light. Not because anything physical is travelling that fast, not because any particle is outrunning photons, but because a shadow isn't a thing. It doesn't have mass, it doesn't carry information, which means it's not bound by the same rules. If you imagine a spotlight shining across a wall and you sweep your hand in front of it, the shadow of your hand can slide along the surface faster than the speed of light if the wall is far enough away. There's no contradiction in that. No law is being broken, because nothing is actually travelling from one end of the shadow's path to the other. It's just a sequence of positions, a projection changing shape. It's a reminder that not everything that moves is really moving, that some things only appear to shift. The motion is an illusion created by the context, the projection of something deeper. The same thing can happen with laser pointers. If you shine one at the moon, which is far away but reachable with a steady beam, and you sweep it side to side fast enough, the red dot can appear to move across the lunar surface faster than light. But that dot isn't a particle. It's the endpoint of many photons, all launched at different angles, each taking its own path. There's no one thing moving across the moon, it just looks that way. This kind of motion, the kind that doesn't transfer anything, is different from what we usually think of as speed. It's not a signal, it's not a cause, it's not a force acting over a distance. It's more like an effect spreading across a canvas. It can seem fast, but it doesn't carry energy or information, and that's where the difference lies. Because in physics, what really matters isn't just how fast something moves, but whether it affects anything at that speed, whether it changes something, whether it can send a message. And that's where the idea of information comes in. Information, in the physical sense, is something that can be measured, transferred, and recorded. It's not just facts or data, it's change. It's the result of interaction. And according to everything we know, no information can travel faster than light. Not even entangled particles can transmit data instantaneously. Their correlation is instant, but you can't use it to send a message. So if you can't use a shadow to communicate instantly, and you can't use a sweeping beam to deliver a signal faster than light, then what you're looking at isn't really superluminal motion. It's just a reflection of geometry, a surface effect, a shifting of angles and patterns, not substance. But these examples, the shadow, the beam, the silent wind, still matter, because they help us understand the difference between what moves through the world and what appears to move. They separate the physical from the perceptual, the real from the apparent, and that distinction becomes even more important when we talk about space itself. See, space isn't a blank stage. It's not a container where things just happen. It has properties. It can stretch. It can bend. And because of that, it can carry things. Not just objects, but changes. When a gravitational wave passes through, for instance, space itself expands and contracts. The distance between 2 points grows and shrinks. You might not feel it, but the wave is real. It's moving through the fabric of reality. But that kind of motion isn't like wind. It doesn't blow. It doesn't push air. It doesn't rustle leaves or stir curtains. It moves everything at once, quietly. You only detect it by comparing very precise measurements, like the lengths of laser beams in observatories like LIGO. And even then, the shifts are tiny, smaller than the width of a proton. This is where motion becomes harder to describe, because if space can move and objects can ride along with it, what does speed mean in that context? It's no longer about going from A to B, it's about the relationship between points that may be changing underneath you. The universe itself is expanding, not just the objects in it moving apart, but the space between them growing. And that expansion can happen faster than the speed of light, because again, nothing is moving through space that quickly. The space is just stretching, and the objects are being carried with it. Galaxies on the far edge of our observable universe are receding from us faster than light, not because they're moving that fast on their own, but because the space between us is increasing at that rate, and light from those galaxies may never reach us. They're beyond what's called our cosmic horizon, outside the sphere where light can travel in the age of the universe. We'll never see them. Not because they're hiding, but because their signals will always be outpaced by the expansion. It's another reminder that speed, in the larger sense, isn't always about motion. Sometimes it's about change happening in the background, silently, persistently, invisibly. That's why the idea of silent wind is more than just a metaphor. There are things that move, or shift, that don't make sound, that don't stir the world in ways we can detect easily. They don't break the rules, they don't shout, they just keep going. Even light is silent. You never hear it coming. The sun's light reaches you across millions of miles, but it arrives without a whisper. It fills the sky with colour and warmth, but you don't hear it until something else converts its energy into sound. A tree rustling, a surface heating and cracking, a voice that light allows you to see. And in that way, the fastest things we know are also the quietest. That silence isn't emptiness. It's just a different kind of presence. Which brings us back to the question, is speed always what it seems? Maybe not. Maybe speed, as we experience it, is limited by what we can perceive, by what we can interact with. But the universe might contain kinds of motion we can't trace directly. Not motion that violates laws, but motion that sidesteps our tools. That doesn't use particles, that doesn't use signals, just motion of form, of space, of relationship. It's hard to study what you can't catch, but physics has always been about looking for footprints, watching how things react, watching what changes. Even when we can't see what's causing the shift, we can sometimes measure its influence. That's why people keep searching, not because they expect to find a particle zipping past light at double speed, but because they're open to the idea that our picture isn't complete, that there could be new kinds of motion, new kinds of change, and maybe even new definitions of speed. Light feels like it should always be first. It races ahead, shows us the way, arrives before anything else does. We use it to measure time, distance, even speed itself. So the idea that light might ever lag behind something, even for a moment, seems wrong, or at least unexpected. But in certain places, under very specific conditions, that's exactly what happens. Light doesn't always move at its full speed, not in every material, not in every situation. In fact, light only reaches its famous top speed, about 300,000 kilometers per second, in a perfect vacuum. That's space with nothing in it. No particles, no fields, just emptiness. Put light into anything else, water, glass, even air, and it slows down. That might sound surprising. After all, when you turn on a flashlight, the beam doesn't seem sluggish. When sunlight enters a room, it looks instant. But at the microscopic level, light passing through a material gets interrupted. It doesn't just sail through like a ghost, it interacts. In water, light moves at about 3/4 its maximum speed. In glass, it slows even more. That's why lenses work, why they bend and focus beams. The light isn't just redirected, it's delayed slightly as it passes through. Now, it's important to say that the individual photons, the fundamental particles of light, aren't stopping and starting. They're not being absorbed and re-emitted in some bumpy manual way. That's a common simplification, but the real picture is more subtle. Light, as a wave and a particle, moves through the material in a kind of collective interaction. The atoms and the electromagnetic field around them influence how the wave travels. The result is that the light behaves as if it's moving more slowly. The front edge of the beam is delayed. It's not because the photon is tired, it's because the environment gets in the way. And here's where it gets even stranger. Scientists have found ways to slow light down dramatically, not just by putting it in denser materials, but by using techniques in quantum optics to interfere with how atoms absorb and emit light. Under the right conditions, they've slowed light down to a few meters per second. In some experiments, they've stopped it altogether, storing the light in a cloud of atoms, and then releasing it again later. It's not permanent. It's not the kind of stop you'd use for travel, but it shows that light isn't always in a hurry. It can linger, if the rules are arranged carefully enough. And yet, in all of these cases, it's not breaking the universal limit. The speed of light in a vacuum, often written as c in equations, remains untouched. That's the true boundary. The variations we see are due to the medium, not the light itself changing its fundamental nature. But still, it raises a question. If light can be delayed, is it possible for something else to get ahead of it? That's where we start to encounter odd situations. Not violations of the laws we know, but edge cases. Events where light is not the messenger we expect it to be. Where it falls behind. One example is in certain types of nuclear reactions. In a specific kind of medium, a charged particle can actually travel faster than light in that medium. Not faster than the vacuum speed, but faster than what light is currently managing inside that material. When that happens, the particle gives off a kind of glow. It's called Cherenkov radiation. You can see it in nuclear reactors, that eerie blue shimmer in water around radioactive fuel rods. It's not because the water is glowing on its own. It's because particles are moving faster than light can move through the water, and the result is a kind of optical shock wave, like the light version of a sonic boom. So even though nothing's breaking the ultimate speed limit, light isn't leading the way anymore. It's playing catch-up. The particle has already gone by. It's a rare thing, and it depends entirely on the conditions, but it shows that light isn't always the fastest messenger in every context. Another example comes from astronomy. When stars explode in supernovae, they can send out both light and neutrinos. Neutrinos are tiny, nearly massless particles that barely interact with anything. They pass through matter almost unhindered. So when a supernova goes off, neutrinos often reach us before the light does. Not because they're faster in a vacuum, they're not, but because the light gets stuck for a while. It bounces around inside the dense cloud of material left by the star, struggling to escape. The neutrinos just pass through and keep going. When a supernova in the Large Magellanic Cloud exploded in 1987, we detected neutrinos here on Earth hours before we saw the light. It wasn't a massive delay. But it was enough to tell us that light isn't always first, that it can be slowed down, that sometimes the quietest particles are the quickest to deliver the news. And that brings us to another angle entirely, the way information moves. In theoretical physics, there are discussions about how signals can be transmitted. What counts as a signal? What qualifies as a real transfer of information? There are experiments that involve pulses of light moving through materials in ways that seem to defy logic, where the peak of a light pulse appears to exit a block before it should have arrived. These are known as superluminal group velocities, but they don't break the rules. No actual information is travelling faster than light. It's a kind of mathematical artifact, a result of how wave packets behave in certain setups. The signal, if you look closely, still obeys the limit. But it's enough to make you wonder, if the patterns can seem to move faster, what about the things we haven't seen yet? The processes we haven't understood? What if there are motions that don't rely on particles at all? There's no evidence yet that information or matter can exceed the speed of light. Every reliable experiment, every confirmed observation says the same thing. The limit holds. But we keep finding examples where light isn't quite as dominant as we expected, where something else gets there first. Neutrinos, shock waves, patterns that race ahead of the beam. So even if light remains the fastest thing in the universe, under the strictest definition, it's not always the first to arrive, not always the cleanest signal, not always the one that finishes the race. And if light can be delayed, if it can linger, then we have to ask what that means for our understanding of space, of speed, of sequence. Because in a universe so dependent on light to show us the way, any hesitation becomes interesting. Maybe that's what makes light so remarkable. Not just its speed, but its patience. It doesn't demand attention. It doesn't insist on being first. It just moves steadily through whatever path is available. Sometimes it races. Sometimes it waits. Sometimes it's blocked and finds another way. And when it arrives, it always brings with it a story from somewhere else. a glimpse of something that happened long ago. If there's a speed limit in the universe, and it seems there is, then somewhere there must also be a trap, a place where that limit isn't just a rule, but a boundary you can't cross, no matter what you do. That place exists. It's real. We call it a black hole. A black hole isn't just an object with strong gravity. It's a region of space where gravity has become so intense that not even light can escape. And if light, the fastest thing we know, can't get out, then nothing else has a chance. That's why people call it an event horizon. It's not a surface. It's not a wall. It's a point of no return. Once anything crosses that line, it's gone from the rest of the universe's view, not because it vanished, but because its signals can no longer escape. The light it emits, the energy it gives off, it all gets trapped. But what's fascinating is how that trap works. It's not that something's physically grabbing the light and pulling it back. It's not a monster reaching out. It's the structure of spacetime itself. Around a black hole, space is curved so sharply that all paths forward lead inward, even the ones that used to lead away. To an outside observer, a beam of light aimed outward from just inside the horizon can never reach the edge. It's like trying to climb up a slope that keeps getting steeper until it becomes vertical, and then inverts. No matter how fast you move, you slide back. Except in this case, there's no sliding. You're just unable to escape. From the inside, things look different. If you were falling in and somehow survived, you wouldn't feel anything unusual at the horizon. There's no bump, no sudden tug. You just keep falling. But from the outside, it would look like time is slowing down for you. As you approach the edge, your motion seems to freeze. Your light becomes redder, fainter, stretched by gravity until it fades entirely. It's not just speed that gets warped, it's time itself. That's what makes the cosmic speed trap so strange. It's not enforced by a force like friction or resistance. It's enforced by geometry. The shape of the universe shifts in such a way that escape becomes impossible, not because you've been stopped, but because all directions now point inward. And in that way, the speed of light becomes more than just a limit. It becomes a gatekeeper, the barrier that defines what's inside and what's out, what can send a message and what can't. But black holes aren't the only places where this happens. They're just the most extreme. The universe has other traps, other boundaries where the speed of light creates limits on what we can know, what we can reach. Take the edge of the observable universe. Light has been travelling since the beginning of time, about 13.8 billion years, and it can only have travelled so far in that time. So the most distant light we can see now comes from a point about 46 billion light years away, due to the way space itself has expanded. Anything beyond that distance, we can't see it, not because it's hidden, but because its light hasn't reached us. And depending on how fast space is expanding, it might never reach us. That means entire galaxies could exist, with stars, planets, maybe even life, and we'll never know. They're beyond the horizon, outside the region where light can connect us. That's another kind of trap, a gentle one, a horizon we didn't build, but one that limits us all the same. It doesn't stop us from moving. It just defines what we can observe, what can affect us. In that sense, the cosmic speed trap isn't a single place. It's a principle. It shows up whenever light's ability to carry information is outpaced by the environment, whether by gravity, by expansion, or by something we haven't discovered yet. And there's a quiet consequence to that. It means we live in a universe where there are places we cannot reach, not just practically, because we don't have the technology, but fundamentally, because no signal we send will ever make it there. No probe, no wave, no message. It doesn't matter how patient we are. It doesn't matter how clever we become. The speed limit creates boundaries not just of travel, but of connection. Even if we were to build a ship that could travel at 99.99% the speed of light, which is already unimaginable, we would still be confined to a small part of the universe, a little island in a sea we can never cross. And that's what makes the speed limit more than just a scientific fact. It becomes something emotional, something existential. Because it means isolation isn't always a choice. Sometimes it's written into the fabric of things, not out of cruelty, just out of structure. Still, there's beauty in that too, because within our horizon, inside the part of the universe we can reach, light connects everything. It binds us to distant stars, to the past, to the remnants of explosions that happened before Earth existed. It lets us see the cosmic background, the soft glow from when the universe was only a few 100,000 years old. And even though it travels fast, it never rushes. It brings things to us in their own time. That gentle pace creates the rhythm of discovery. One photon at a time the universe reveals itself. But even as we learn more, we still bump into the edges, not just because our instruments aren't sensitive enough, but because those edges are real, fixed, unmovable. Some researchers think there may be ways to go around them, not by breaking the speed of light, but by folding space, using wormholes or warping the geometry of space-time itself. If such things are possible, they'd change what we mean by distance, maybe even by speed. But they're still just theories for now, ideas waiting for evidence. So for the time being, the cosmic speed trap stands, not as a punishment, not as a block, just as a part of the structure we live in, a part we can map and stretch toward, but not pass through. Somewhere on the other side of the speed limit, in theory at least, live the particles that shouldn't exist. They're not part of our everyday experience. We've never seen one. We've never caught a trace of their passing. But on paper, they're allowed, not required, just possible. They're called tachyons. The word comes from the Greek tachys, meaning swift, and the name fits. Because tachyons, if they exist, don't just move fast, they move faster than light. Not in a clever workaround kind of way, not as a trick of space or time, but as their default. They never slow down to reach the speed of light, because they don't cross that line at all. They live entirely on the other side of it. That's part of what makes them so strange. Everything we know that has mass can't reach the speed of light. The more energy you pump into something, the closer it gets, but the heavier it becomes. Eventually it needs infinite energy to go just a little bit faster. That's the barrier. Photons, which have no mass, don't accelerate to that speed. They're simply created moving at it. That's their nature. That's where they live. But if tachyons were real, their mass would be imaginary, not just small. Imaginary in the mathematical sense, involving the square root of -1. In most cases, imaginary numbers are tools. They help with equations, especially in quantum mechanics, but they rarely correspond to anything we can point to in the real world. So tachyons are ghosts in more than one way. They exist in the math, but not in any experiment. They can be described, but not detected. And here's the part that makes them even harder to handle. You can't slow them down. You can't bring them to rest. You can't even make them approach light speed from above. Just like objects with real mass can't reach the light barrier from below, tachyons, in theory, can't slow down enough to match it from the other side. That creates a kind of mirror world, one where the normal rules still apply but from the opposite direction. Instead of speeding up as you add energy, a tachyon would slow down. Instead of becoming heavier, it would become lighter. But it could never go slower than light, any more than we can go faster than it. Of course, this raises the question, if they can't interact with us directly, what are they doing in our theories? In some versions of quantum field theory, tachyons show up not because they're real, but because the system being described is unstable. It's like a clue in the math that something's not right, that the vacuum isn't in its lowest energy state. Fix the instability, and the tachyon disappears from the equation. It's not that the particle was ever real, it's that the theory needed to settle down. So in that context, tachyons are a signal, not a substance. a mathematical red flag. Not a prediction, but a correction. Still, some researchers have asked the question more directly. What if they are real? What if, somewhere in the vast spread of space, there are entities that move so quickly we'll never see them, that outrun every signal, that pass through without interacting, not because they're hiding, but because they're simply too fast for us to catch? It's not an easy question to answer, because the faster something moves, the harder it is to detect, especially if it never drops below the threshold of light speed. Our detectors rely on interaction, on particles bouncing off or being absorbed or leaving a trail. Tachyons, if they exist, might glide through matter without leaving a mark. But even if they can't be caught directly, maybe they could leave hints, disturbances, gaps, effects without causes, a kind of signature left behind by something we didn't see arrive. There have been attempts to find such traces. High-energy physics experiments have looked for anomalies, deviations in expected decay rates, unexplained blips in data. So far, nothing stuck. No clear, repeatable sign. Just speculation. And then there's the problem of causality. Because if something can travel faster than light, it can, in the framework of special relativity, send signals backward in time, not from its own point of view, but from ours. You could set up a situation where a tachyon leaves one point in space and arrives at another before it was sent. It's not magic. It's not even a flaw. It's just how the math works when you exceed the speed of light in certain frames of reference. The timeline bends, the sequence reverses, and suddenly you're not just dealing with fast particles, you're dealing with potential paradoxes. Can a message arrive before it was sent? Can an effect precede its cause? Most physicists are cautious here. They point out that just because the math allows something doesn't mean nature does. A theory can have solutions that the real world never uses, and so tachyons stay in the realm of maybe, possible but unlikely, not ruled out, but not confirmed. Still, they're worth thinking about, because they force us to examine the limits of our understanding. They challenge the assumption that the speed of light is not just a rule, but a wall. They open the door to a universe where different forms of motion exist, not just faster, but fundamentally unlike anything we've experienced. And tachyons aren't alone. There are other ghost-like ideas floating at the edge of physics, like virtual particles, particles that exist briefly during quantum interactions, borrowing energy from the vacuum and then disappearing. They're not observable directly, but their effects are real. They help explain how forces work at the smallest scales. They shape the structure of matter, or dark matter, which isn't fast necessarily but is invisible. We can't see it, we can't touch it, but it's there, bending light, shaping galaxies, holding things together. Not because of what it does directly, but because of how the things around it behave. And then there's the idea that the universe itself might contain fields we haven't discovered, structures that don't show up in the standard model, but which influence motion, mass, or time in subtle ways. Ghosts of another kind, not particles, but possibilities. Tachyons are a kind of placeholder, a signpost for the edge of the map. They might not be real, but they mark a question we haven't answered, a direction we haven't travelled, and that makes them valuable. Not because we expect to meet them, but because thinking about them reminds us how much we don't know. What if speed isn't limited in the way we think it is? What if light is only the fastest thing we can measure? And what if, out there, somewhere, there are currents moving faster, deeper, colder than anything we've detected? We don't know. But the question leads somewhere. There's a place in physics where a distance seems to lose its meaning, where two things, no matter how far apart, act like they're still connected, not by a wire, not by a beam of light, but by something stranger, something that doesn't travel, something that just is. It's called entanglement. When two particles are entangled, they share a state. You can measure one and instantly know something about the other. It doesn't matter if they're a few inches apart or on opposite ends of a galaxy. The connection holds, not like a signal, not like a transmission, just an outcome that stays balanced, even when the pieces are nowhere near each other. It feels like it should break the rules, especially the one about speed, because nothing, we're told, can influence something else faster than light, and yet here are these particles, electrons, photons, atoms, behaving as if they're still part of the same system, even when all communication should be impossible. So what's really happening? First, it helps to understand what entanglement means in the quantum sense. It's not just a link, it's a shared state. When two particles are entangled, their properties, spin, polarization, momentum, become part of a single mathematical description. You can't describe one without describing the other. This doesn't mean they're identical, it means they're correlated. If one spins up, the other spins down. If one tilts left, the other tilts right. But those directions aren't locked in from the beginning. Not in the classical sense. They exist in a kind of superposition, a blend of possibilities, until you measure one. And here's where the weirdness begins. When you do measure one, its state becomes definite, and instantly, without delay, the other particle's state becomes definite too. Not because a message passed between them, but because the entangled system requires it. It's not that one particle tells the other what to do. It's that the two are part of the same unfolding event, no matter the space between them. Einstein didn't like this. He famously called it spooky action at a distance. To him, the idea that measuring something here could affect something there instantly was unacceptable. He thought there had to be hidden variables, something underneath the surface determining the outcome in advance, a kind of secret script that made the results look coordinated, even if they weren't. But over time, that idea didn't hold up. Physicists designed experiments, starting in the 1960s with John Bell's work, that tested whether such hidden variables could exist. The results, again and again, showed that entangled particles violate something called Bell's inequality, which means essentially that no hidden script can explain the correlation. The outcomes really are linked in a way that's fundamentally quantum. Still, as strange as that sounds, there's a limit. Entanglement doesn't let you send information faster than light. You can't use it to send a message. Because even though the measurements are correlated, the results are random. You can't control what result you get, only observe it. And so there's no way to transmit a specific signal using just entanglement. That's what keeps causality safe. No paradox, no backward time loops. Just a peculiar, non-local connection between two things that were once part of the same whole. And yet, the instantaneity of it still makes people pause. Because in every other part of physics, cause and effect depend on motion, on influence spreading from one point to another at a limited speed. Even light, for all its quickness, needs time to arrive. But entanglement doesn't seem to wait. It doesn't need a medium. It doesn't fade with distance. You could separate entangled particles by kilometers, or even light years, and the correlation remains. That's not motion. That's something else. Some physicists think this is a sign that space itself might be an illusion, or at least not as fundamental as we think. That the underlying reality isn't shaped by distance, but by relationships. That entanglement isn't about particles reaching across space. It's about two parts of the same system being revealed, one piece at a time. If that's true, then speed doesn't matter, because nothing is travelling. There's no crossing of space, just a coordination that's already in place. It's like flipping two coins that always land opposite, heads and tails, but only because they were made that way together. The result feels instantaneous, but only because the connection was built in from the beginning. You're not seeing a signal, you're seeing structure. Of course, quantum systems aren't that simple, and the analogy only goes so far, but it does help to shift the way we think about interaction. Maybe not everything needs to move to connect. Maybe some connections are baked into the setup. Not physical strings, but shared conditions. Not speed, but symmetry. And that symmetry might run deeper than we realize. Some researchers believe that entanglement isn't just a feature of quantum mechanics. it might be the foundation of space-time itself, that the geometry of the universe, the fabric of space and time, could emerge from networks of entangled particles. If true, it would mean that entanglement isn't a violation of space, but the source of it. That's speculative, it's a young idea, but it fits with something people have suspected for a while, that the fastest thing in the universe might not be speed at all, it might be relationship. That's hard to picture, especially when everything we know is rooted in motion, in things going from here to there. But entanglement asks us to think differently, to imagine a kind of instant that doesn't need a journey, a kind of closeness that isn't about proximity but about connection. And in that framework, faster than light becomes a strange phrase, because it assumes there's travel, that there's a start and an end. But entanglement has no path, no signal, no in-between. It just is. And yet it gives us a glimpse of something beyond our usual limits, a hint that not all interaction depends on speed, that not all cause needs a vehicle, that maybe, just maybe, the universe allows certain things to be bound without being bridged. We don't know what that means yet. Not fully, but we're getting closer. We think of space as something still, a backdrop, a quiet canvas stretched beneath the movement of stars and galaxies. But it isn't. Space itself is expanding, not as an explosion, not as something spreading into emptiness, but as a process that happens everywhere, all at once, all the time. And here's the surprising part, that expansion is moving faster than light. That doesn't mean galaxies are rocketing through space at superluminal speeds. It means that the space between them is stretching so rapidly that the total distance increases faster than light could travel. It's not a trick, it's not a loophole, it's something allowed, even required, by the structure of the universe itself. When we look out into space, we're also looking back in time. The farther we see, the older the light is. And beyond a certain distance, that light won't reach us at all. Not because we're not patient enough, but because the space between us and the source is growing too quickly. Every second it pulls that light farther away, and eventually even the fastest signal in the universe can't keep up. There's a name for that invisible edge, the cosmic horizon. Everything beyond it is receding from us faster than light. Not because it's moving through space at that speed, but because the space itself is expanding that fast. Like dots on the surface of an inflating balloon, they're carried apart not by their own motion, but by the swelling of the fabric beneath them. This doesn't violate relativity. The rule that nothing can move faster than light only applies to objects through space, not to space itself. General relativity, which describes gravity and the curvature of space-time, allows for this kind of expansion. And in fact, it predicts it. So when we say the universe is expanding faster than light, we're not talking about speeding vehicles. We're talking about distance changing in a way that makes light itself fall behind. In practical terms, it means there are galaxies we will never see. Light left them billions of years ago, but the distance between us and that light has been growing ever since, and growing faster than the light can close it. So it never arrives, it never catches up. And there are more galaxies like that every day. Even some that are visible now, just barely, will someday fade from view, not because they're getting dimmer, not because they're moving away in a straight line, but because the expanding space between us will stretch their light until it's too faint, too red, too far gone to detect. Eventually, if the expansion continues, or accelerates, as we suspect it is, there will come a time when only a small region of the universe remains visible from Earth. Everything else will lie beyond the reach of light, and then, from the perspective of an observer far in the future, it will seem like the universe is shrinking. Not because the space is collapsing, but because the window of observation has closed. That's the strange consequence of faster-than-light expansion. It's not just a measurement, it's a limit on knowledge. It defines what we can see, what we can test, what we can confirm. It draws a boundary, not with a wall, but with time. And no matter how fast we move or how powerful our tools become, that boundary holds. This might sound discouraging, but it's also what makes cosmology so remarkable. Because even within that shrinking horizon, light still reaches us. Old light. Ancient light. Photons that have been travelling for billions of years, stretching and dimming as they move. And when they finally arrive, they carry the shape of the early universe. A map of what things looked like just after the Big Bang. That light forms the cosmic microwave background, and it's one of the clearest windows we have into the beginning of everything. It's the oldest thing we can see, and also one of the most detailed, so even as expansion outruns light, light still outruns time. It preserves the record, it carries the signal. It's not fast enough to escape expansion forever, but it's fast enough to give us a glimpse before the door closes. And in that glimpse, we learn something else. The expansion isn't steady. It changes. It's affected by gravity, by matter, by dark energy, an unknown force that seems to push everything apart. Right now, dark energy dominates, and because of it, the expansion is accelerating. That means the faster-than-light separation is getting worse. The cosmic horizon is shrinking. The window is closing. More and more of the universe is being carried beyond reach. Again, this doesn't mean things are flying apart in an explosion. It means the metric, the measure of distance, is changing, stretching. And that stretching makes the universe feel like a place where limits are baked in, not because of speed, but because of the ground we're standing on. And yet, this kind of faster-than-light motion isn't a violation. It doesn't break the rules. It just changes the rules' context. Because when space itself is in motion, the rules that apply to objects in space don't cover the full picture anymore. A car can't go faster than the road allows. But if the road itself begins to stretch, the car's distance from the start grows whether it's moving or not. Add enough stretching, and the car outruns any signal sent behind it, not by driving, but by staying still on a shifting surface. That's what galaxies beyond our reach are doing. They're not racing away. They're riding the fabric of space as it expands. It's a quiet kind of motion, one we can't feel, one we only notice because the signals from distant places no longer arrive, a silence that deepens slowly, year by year. And so the fastest movement in the cosmos might not be the speed of a particle or a flash of light. It might be the way space itself carries things beyond the edge of knowing, not with force, not with noise, just with steady distance increasing until even the light can't keep up. If space can stretch, maybe it can bend, and if it can bend, maybe it can fold. That's the idea behind wormholes. Not roads through space, but bridges between places. A shortcut. Not because anything moves faster than light, but because the distance itself is made smaller. Picture a piece of paper. Draw two dots at opposite corners. The usual way to travel from one to the other is across the surface. A straight line, sure, but still a distance. Now fold the paper so the two dots touch. Suddenly the path is gone. You're there already. Not by speed, just by geometry. That's the basic picture of a wormhole. It's a theoretical passage connecting two separate regions of spacetime. Not like a tunnel through a planet, but a bridge through space itself. It could connect two distant points in the same universe. Or maybe, depending on the math, two entirely different universes, two timelines, two dimensions. We don't know. We've never seen one. But the equations that describe gravity, Einstein's general relativity, allow them. In fact, one of the earliest exact solutions to Einstein's field equations, written down in 1916, describes something that looks a lot like a wormhole. It's called the Einstein-Rosen bridge. At first it seemed like a mathematical curiosity. Later, physicists realized it could connect two black holes, or two openings, through a hidden corridor of curved space. But there's a catch. Actually, there are several. Most wormholes, if they exist, collapse too fast to pass through. They pinch off before anything can get across, even light. The tunnel never stays open. It forms, it folds, and then it vanishes. To hold a wormhole open, you'd need something exotic, matter with negative energy. Not just less than zero, but actually opposite in behaviour. It would have to resist gravity instead of obeying it. It would push out instead of pulling in. In ordinary physics, that kind of matter doesn't exist. But in quantum theory, there are situations where negative energy can briefly appear, in the gaps between particles, in the vacuum fluctuations of empty space, tiny fleeting effects, not enough to build a tunnel, but enough to keep the idea alive. So the question becomes, could these quantum effects, if controlled or scaled, stabilize a wormhole? Some researchers think maybe. Not now, not soon. But in theory, it's not impossible. And if such a bridge could be made, or found, what would it mean for speed? Well, nothing would be breaking the speed of light. Light would still move along its normal path, at its normal speed. But the path itself would be different, shorter. So from the outside, it might look like something jumped from one end to the other instantly. Not because it travelled fast, but because it didn't have to travel far. That's why wormholes are sometimes discussed in connection with faster-than-light ideas. They don't actually speed anything up, they just change the shape of the route, and that change has implications. If you could pass through a wormhole and emerge somewhere far away, you'd be able to beat light to that location. At least from the point of view of someone who stayed on the outside, you'd seem to have travelled faster than physics allows. But really, you just took a path light couldn't follow. It's still speculative, and it raises more questions than answers. What keeps the tunnel stable? Could anything survive the journey? Would the ends of the wormhole stay fixed or drift? Could it be used for communication, not just travel? And, perhaps most strangely, would it allow time travel? Because if one end of a wormhole moves differently than the other, time itself could be offset. You could enter one mouth and exit before you started. Again, the math allows it. But we have no way to test it, no evidence that it can actually happen. Still, the idea won't go away. Not because we expect to find a wormhole next door, but because it offers a glimpse of what might be possible in a universe where space isn't rigid, where distance isn't absolute, where geometry can be shaped, not just by matter, but by understanding. It's also a reminder that speed isn't always the limit. Sometimes the structure itself matters more than motion. If you can change the shape of space, you change what's possible within it. That's part of what's behind more recent ideas, like the Alcubierre drive, a theoretical concept where a spacecraft rides a bubble of warped space. It wouldn't move through space faster than light, but space itself would move, contracting in front, expanding behind, carrying the ship forward like a current. Again, speculative. Again, rooted in equations that don't violate relativity. But again, requiring forms of energy and control we don't yet have. Whether wormholes exist or can be made is still an open question. But the fact that they're allowed, even tentatively, suggests something important. That the universe might not be closed off in the ways we assume. That distance, speed, and time are not always fixed. They depend on shape, on structure, on the quiet, flexible geometry of space-time. So maybe the way to reach somewhere fast isn't by pushing harder. Maybe it's by finding or forming a better path. Not all shortcuts are about speed, some are about design. Information moves differently than matter. It doesn't have weight, it doesn't have shape, but it does have rules. You can't copy it perfectly, you can't destroy it entirely, and according to everything we know, you can't send it faster than light. Still, we keep asking, can information beat the clock? It's not a strange question if you think about it. Because when something changes, when something happens, what we really care about isn't the object, it's the news of the object. Did it shift? Did it break? Did it arrive? Those aren't just physical events, they're messages, ripples in understanding. What matters is when the information reaches you, and that's where light, again, becomes the standard. Light is how we see, it's how we measure, it's how we detect. It doesn't just carry brightness, it carries meaning. Everything we know about a star, a supernova, a galaxy far away, it all comes in the form of light. Even in particle detectors, where we're not using our eyes, the tools still rely on signals travelling at or below the speed of light. So what happens when we ask whether information itself, stripped of mass, stripped of form, could go faster? In most cases the answer is no, because even the most immaterial signal still needs a carrier, a wave, a particle, a field, and that carrier, whatever it is bound by the speed limit. You can't whisper across the universe without something to carry your words, and nothing we know of moves faster than light. Not neutrinos, not gravity, not even quantum fields. They all obey the same ceiling. But there are some edge cases that make the question harder. Take quantum entanglement, which we touched on earlier. When two particles are entangled, measuring one seems to affect the other instantly. It's a correlation, not a signal, but it still feels like information. One particle knows what the other is doing, even from light years away. But that's not quite right, because you can't use it to send a message. You can't control the outcome. The measurement on your side is random. You only see the pattern when you compare notes later. And that note sharing still requires a normal signal, one that travels slower than light. So the instant connection doesn't violate the limit. It just makes us wonder what information really is. Is it only a pattern we recognize after the fact? Or is it something more fundamental, something built into the structure of reality itself? There are other curiosities too. In certain materials, under precise conditions, waveforms can appear to move faster than light. Not the energy or the signal, but the shape of the wave. The group velocity, as it's called. But that doesn't carry usable information. It's more like a mirage. The peak of the wave shifts, but no message gets through faster than the limit. Or consider hypothetical particles like tachyons. If they existed, and if they could be used to transmit data, then yes, information could beat the clock. But as we've seen, tachyons aren't part of any confirmed theory. They remain speculative, and even if they did exist, sending usable, organised information through them would create all sorts of causality problems, effects before causes, messages from the future, paradoxes. Which brings us to a deeper point. Causality is protected by the speed of light. It's not just a rule about motion. It's the structure that keeps time moving forward. If you allow information to travel faster than light, you allow time to fold. Not the poetic kind of time travel, but logical reversals. Events happening before their causes. A universe where the future can influence the past. Most physicists see this as unacceptable, not because it's hard to imagine, but because it breaks the internal logic of everything we observe. The equations that govern motion, fields, entropy, they all assume cause comes before effect. Break that, and the system falls apart. So for now, the answer holds. Information can't beat the clock. But that doesn't make the question meaningless, because thinking about it forces us to consider what information really means. Is it just a signal between 2 points, or is it something that shapes reality itself? In black hole physics, for instance, there's a major mystery about information. What happens to it when something falls into a black hole? Is it lost forever? If so, that would violate a basic principle of quantum mechanics, that information must be preserved. Even if it's scrambled or hidden, it can't disappear. One idea is that the information is stored at the surface, the event horizon, encoded in tiny fluctuations like pixels on a screen. Another idea is that it gets released slowly through Hawking radiation, particles that escape the black hole over time. If that's true, then information doesn't move faster than light, but it also doesn't stay trapped. It just takes its time to come back. That's one of the reasons physicists talk about the holographic principle, the idea that everything happening in a volume of space, could be described by information stored on its boundary. It's not proven, but it hints at a different way of thinking, that information isn't something that moves, but something that is. Not a passenger, but a framework. In that light, no pun intended, the question isn't just whether information can move faster than light, it's whether movement is even the right concept at all. Maybe information doesn't travel, maybe it emerges, maybe it unfolds, not across distance, but across change. And the light speed limit applies not to the information, but to the events that let us notice it. That still leaves the boundary in place, but it shifts where we think the limit applies. It's not just about speed, it's about awareness, about the pace at which the universe allows understanding to happen. And so, when we ask whether information can beat the clock, we're really asking whether knowing can happen ahead of experience, whether the future can speak before the present arrives. So far the answer is no. But it's a gentle no, not a slam. Just a quiet reminder that timing is part of the design. That light isn't just a cap, it's a rhythm. When something moves faster than light, if such a thing exists, you wouldn't see it coming. You wouldn't hear it either. It would outrun its own signal, leave no wake, no warning, just a presence after the fact, already gone by the time you noticed it was there. That's the silence of the superluminal. In the world we know, speed brings noise. A jet rips through the air and leaves a roar behind. A train clatters and rumbles. Even fast thoughts feel sharp. Quickness is something we associate with force, with contact, with change. But the kind of speed we're talking about here, the kind that breaks the barrier of light, doesn't behave like that. If it exists, it lives in quiet. It doesn't push. It doesn't announce. It simply happens, too quickly for detection. Even the idea of such motion feels slippery. Because everything we use to notice things, our senses, our instruments, our theories, is tuned to signals that move at or below the speed of light. Faster than that, and the rules stop working. The frameworks bend. Not broken, but no longer useful. You can't photograph something that arrives before its image. You can't hear something that passes before it vibrates the air. You can't touch something that doesn't slow down enough to interact. So if there's anything in the universe that moves faster than light, it would exist, to us, in a kind of invisibility. Not the cloaked kind, just a natural absence of contact. This is part of why superluminal motion, even as a concept, is so elusive. It's not just fast, it's unreachable, and in most cases, unprovable. Still, the idea shows up, not just in science fiction, but in real physics. We've talked about tachyons, hypothetical particles that, if they exist, always move faster than light, never slowing, never dipping into our visible world. The math says they could be there, but we don't know how to find them, because their path avoids every tool we've built to observe, or consider shadows and laser beams sweeping across distant surfaces faster than light would. These are illusions, of course. No actual object is travelling superluminally, just patterns, effects, geometries that give the appearance of speed without any information actually crossing the gap that quickly. But the silence remains, because what we learn from these cases, even the harmless ones, is that superluminal motion isn't just fast, it's disconnected, it leaves no usable trace, and it doesn't carry meaning the way slower motion does. There's a story buried in that. In physics, speed without information is like a book with blank pages. It moves, but it says nothing. It's not a message. It's just an event, untethered to understanding. That's why the light speed limit is more than just a number. It's the boundary between what we can interact with and what we can't. Between what we can know and what we can't even frame a question about. Superluminal speed, if it exists, lies outside that frame. Not because it's forbidden, but because it leaves us out of the loop. And yet, not all superluminal effects are illusions. Some are real, in the sense that they happen within known physics, even if they don't involve faster than light travel. Gravitational waves, for example, spread at the speed of light, but the stretching of space that produces them, that's not a wave through space. It's space itself changing. It's subtle, but it matters. In the early universe, during what's known as the inflationary period, space may have expanded exponentially faster than the speed of light. Not objects in space, but the very fabric of it. If true, that expansion smoothed and shaped the universe we live in today, and we wouldn't be here without it. So, again, the silence of the superluminal isn't about absence, it's about form. When things move faster than light, they don't leave trails we can follow, but sometimes they leave a shape, a pattern, a footprint, however faint. That's what scientists look for now. Not the thing itself, but the shadow it might have cast. Not the voice, but the ripple left by its passing. And sometimes what's most revealing is what we don't see. The silence becomes its own kind of data, an absence that hints at something just out of reach, something not broken, just too fast. It's like trying to listen to a bird that flies overhead before its song reaches the ground. You don't hear it until it's already far away. The sound falls behind the motion, and even then, you can only guess where it came from. That's the best metaphor we have for superluminal motion. Not noise, but lag. Not message, but delay. And so, when we talk about the silence of the superluminal, we're really talking about what it would mean to exist beyond contact, beyond confirmation, in a realm where nothing reflects back, where signals can't catch up, where knowledge, even in principle, cannot follow. And yet, even here, the mind reaches, gently. We imagine what might live in that silence. We ask what kind of universe allows things we can never see, not to escape the laws we know, but to expand the picture, to admit that silence might be part of the song. We call it the speed of light, a constant, a limit, a number we build our measurements around. In a vacuum, it moves at just under 300,000 kilometers per second, fast enough to circle the Earth 7 times in a single second. Unimaginably quick, yet precisely predictable. But light doesn't always move that fast, not everywhere, not through everything. Under certain conditions, it slows down. That might sound impossible. How can the fastest thing in the universe not always be at its fastest? And yet, this is something we've observed many times, in many places. Not a flaw in the theory, just a feature of how light behaves when it travels through anything other than empty space. In glass, it moves more slowly than it does in air. In water, slower still. In some materials, carefully prepared in the lab, we've made it crawl. In one famous experiment, researchers passed light through a cloud of ultra-cooled atoms and slowed it to just a few meters per second, the pace of a brisk walk. In another, they stopped it entirely for a moment, and then restarted it again. It wasn't frozen like a snapshot. It was more like the light's properties, its information, were stored in the medium itself, held in place, waiting to resume. None of this breaks the rules of relativity, because what we call the speed of light, the universal limit, refers specifically to its speed in a vacuum. When we say nothing can go faster, that's what we mean. Nothing can move through empty space faster than a photon does. But when light travels through a medium, any medium, it's affected by that environment. It interacts. That's what causes the delay, not because the photons are getting tired or bumping into atoms like tiny billiard balls. It's subtler than that. The electromagnetic wave that makes up the light induces vibrations in the electrons of the material. Those vibrations, in turn, generate new waves that combine with the original one. The result is a kind of forward motion that, from the outside, looks slower than what you'd see in a vacuum. So the light isn't changing its essential speed, it's dealing with interruptions. It's like a messenger walking through a crowded room. They're still trying to move forward, but each step is adjusted, nudged, influenced by the crowd. They arrive later than they would have in an empty hallway, but not because they forgot how to move, because the space itself required a different rhythm. And this change in speed is what gives rise to things like refraction, the bending of light as it moves from one medium to another. It's why lenses work, why magnifying glasses enlarge, why rainbows spread out in arcs across the sky. Each wavelength of light slows down by a different amount in a material, and that difference creates the separation of colours. So slowing light isn't just possible, it's ordinary. It happens every time you look through glass. But when you stretch this idea, slow it down further, shape the environment even more, you begin to see how flexible light really is. In highly controlled experiments, we can use laser-cooled atomic vapours to bring light to a near halt. In these setups, physicists use what's called electromagnetically induced transparency, a way of manipulating how atoms absorb and transmit light. With the right arrangement, they can create conditions where light pulses enter, stop, and then resume their journey with the same shape and information intact. What's being held isn't just the beam, it's the pattern, the encoded information that defines the light structure. That information in some sense is preserved even when the light itself isn't moving, and that preservation raises new questions. Because if light can be slowed, paused, stored, and restarted, then what does that say about its role as the universal messenger? Is speed still the defining trait, or is it adaptability? Light moves fast in a vacuum, yes, but more than that, it adjusts, it reshapes, it accommodates the environment it travels through, and in doing so, it continues to carry meaning, even when the journey isn't quick. So perhaps what makes light remarkable isn't just its top speed, but the fact that it still functions when slowed, that it continues to communicate even when the pace is not what we expect. There's also something calming in that, because we tend to associate delay with failure, with weakness. But here, delay is part of the design, a sign of interaction, a signal that something real is happening, that the light is not just passing through, but responding to its surroundings. That kind of responsiveness shows up in more than just optics. It appears in communication systems, in fibre cables that slow and guide light to deliver signals across the world, in sensors that detect changes in light's path as a way of understanding the environment. Even in your body, light, in the form of photons, is involved in processes where speed is only part of the story. Your eyes take in light, but the signal it creates takes time to reach the brain. The image forms in steps. You don't notice the pause, but it's there, and it doesn't reduce the meaning. If anything, it adds to it. It gives the image depth, sequence, time to settle. So maybe we don't always need things to move at their fastest. Maybe what matters more is that they carry the message well, whether it arrives instantly or with pause, whether the beam flashes ahead or takes the long way around. Light slower than itself is still light, still the same wave, the same energy, the same story, only delayed. And sometimes that delay gives us something new to notice, a bend, a spread, a chance to see how motion and matter shape each other. It's easy to forget that even the fastest things have moments of patience. We talk so much about light, its speed, its clarity, its ability to reveal what was hidden. But darkness moves too, not with a flash, not with a beam, but with absence. And it's tempting to ask, if light has a speed, does darkness? The question sounds like a riddle, like something a child might ask while staring out of a window at dusk. And yet, in physics, it's a fair question, because darkness isn't a thing, it's what's left when something else is gone. It's not an object, it's a result. Still, it behaves in ways that suggest motion. You can see it in a shadow that shifts across a wall, in a night that rolls in when the sun dips below the horizon, in the dimming of a room when a light turns off. In each case, something changes, and that change moves. But what's actually travelling? Not darkness itself, not as a particle, not as a wave. What moves is the boundary, the transition from light to dark, the point where light stops arriving, and that point, depending on the situation, can move very quickly, even faster than light. That might sound like a contradiction, but it isn't, because the edge of a shadow, or the spread of nightfall, isn't caused by something travelling. It's caused by something no longer arriving, a beam cut off, a source blocked. And when that absence sweeps across space, the line it draws can move without the constraints that limit actual signals. Think of it like this. If you shine a laser pointer across a vast distance, say, onto the surface of the moon, and then sweep your hand, the dot of light can move across the lunar surface incredibly fast. Depending on the distance and the angle, it could move faster than the speed of light, but the dot isn't a physical object, it's a changing point of contact. Nothing actually travels along that path. No single photon goes sideways across the moon's face, it's just where the photons are landing, and where they're not. The same logic applies to darkness. The speed of darkness is just the rate at which a lack of light reaches new places. It's a subtraction, not an addition, an unfilling of space, and that makes it slippery to define. But it still has effects. In eclipses, the shadow of the moon races across the Earth at high speed, thousands of kilometers per hour. It's not because the moon is moving that fast, but because the geometry of the light, the angles of the Earth and the Sun, combine to create a sweeping edge of darkness. It's real, it moves, and you can predict its arrival down to the second. Astronomers use this to their advantage. They observe how stars dim as objects pass in front of them. Planets, dust, debris. All of it creates a kind of moving darkness. And from that, they learn about the object doing the blocking, its size, its speed, even its atmosphere. The darkness isn't empty, it's informative, it carries shape. Even in day-to-day life you witness this. When headlights pass by and a shadow leaps up a wall. When a person walks in front of a screen and their silhouette ripples across the room. That movement isn't made of anything. But it still happens. It's coordinated. It arrives and leaves like any other motion. So while darkness isn't a substance, its movement isn't meaningless. It's a measure of change, a reflection of what was removed. And just as light can reveal, darkness can conceal. Selectively, temporarily, precisely. Not in malice, just in geometry, in perspective, in angles of approach. In physics, we sometimes talk about the propagation of a null signal. Something that isn't there, but whose absence still moves in a coherent way. That's not poetry. It's part of how fields and detectors interpret changes. A null pulse, a drop, rather than a spike, and that drop spreads. It follows rules. It has a front. So can darkness have a speed? Technically, no, not on its own, not as a travelling entity, but the boundary between light and dark, that can move, that can spread across a surface, that can leap from one place to another, carrying with it a shift in what we can see and how. In that sense, darkness is reactive. It tells us not just what's missing, but what just changed. It's also a reminder that visibility is local. You can only see what light reaches you. Everything else is in shadow. And that shadow isn't permanent. It depends on the position of the sources around you, on time, on distance, on whether something blocks the way. And sometimes, the absence tells us more than the presence. In astronomy, the most interesting things are often the ones that aren't directly visible. Black holes, exoplanets, cold gas clouds. We know they're there not by the light they give off, but by the light they block, by the silence, by the darkness that moves when they move. It's a different kind of data, but it's still data, so maybe the speed of darkness isn't about motion at all. Maybe it's about recognition, about the rate at which awareness fades, or shifts, or moves from one region to another, carried not by photons, but by their absence. A sunset isn't a thing moving across the land, it's the edge of illumination withdrawing, and yet it feels like movement. It feels like something happening, and so, as with light, the story isn't in the thing itself, it's in the change. We live in a world that often treats speed as a virtue. The faster we go, the more efficient we seem. The quicker the result, the more advanced the system. In technology, in communication, even in thought, speed is celebrated. It looks like progress. It feels like improvement. But is it? Does going faster always mean we're going forward? In physics, speed is just a measure. It tells us how much distance is covered in a certain amount of time. It doesn't say why something is moving, or where it's headed. It doesn't measure value or purpose or understanding. It's just motion. That alone isn't progress. In the vacuum of space, an object can hurtle endlessly at incredible velocity and never change anything. It might be fast, it might be impressive, but unless it interacts, it leaves no trace, no cause, no result, just motion without context. We see this in galaxies drifting apart as the universe expands. The speed of separation grows, but the direction doesn't change. There's no destination, just distance increasing, automatically, quietly. And we see it in the smallest things too. Particles in a hot gas fly around faster than those in a cold one, but they're not going anywhere. They're bouncing, jostling, exchanging energy, a chaos of movement with no clear path. It's not aimless. It follows the laws of thermodynamics, but it doesn't move the system toward a goal. It's just a statistical blur. So if speed doesn't guarantee progress in nature, why do we assume it does in our own lives? Part of it is habit. We notice when something is faster. It grabs our attention. A quicker response, a shorter wait, a higher number. It suggests improvement, even when we don't ask what's being improved. But not everything gains value by going faster. A rushed explanation can miss the meaning. A fast answer can skip the question. Even a quick solution can fail if the problem it solves was the wrong one to begin with. Progress, it turns out, isn't just about movement. It's about direction, about depth, about whether the change leads to something better or just different. And sometimes the fastest path misses the most. In physics, we learn that speed and observation don't always get along. The faster something moves, the harder it becomes to measure precisely. Relativity tells us that time and length change with speed. The faster you go, the more distorted your view becomes. At extreme velocities, clocks slow down, lengths contract, causality gets rearranged. It's not an error, it's a built-in feature of how space and time behave. But it reminds us that high speed doesn't just bring you to new places, it changes how you experience the places you arrive at. And sometimes, to truly understand something, you have to slow down. A distant star may flicker fast, but it takes time, years, decades to gather its light. A slow, careful scan can reveal a planet orbiting nearby, or a dust cloud moving in front. Those changes are not dramatic, but they build up, they inform, they clarify. In science, most breakthroughs come slowly. They emerge from patient observation, from long hours of comparison, repetition, revision. Even the most exciting discoveries are often the result of decades of quiet data. And in nature, some of the most efficient systems are slow by design. Trees grow over years, not seconds. But in that time, they build structures that last for centuries. They convert sunlight into sugar, carbon into strength, with no rush, only balance. Geological processes move even slower. Plate tectonics, mountain formation, the erosion of rock into sand. These changes are invisible to the daily eye, but they shape the planet more than any quick impact ever could. So maybe the question isn't whether speed means progress, but whether we've confused pace with purpose. Fast doesn't always mean forward, and slow doesn't always mean behind. In fact, some things only make sense when you don't hurry them. Listening, learning, healing. These aren't quick actions. They take time, not because they're inefficient, but because they involve change that moves through layers, through complexity, through things that don't yield all at once. And in physics, again, the speed of light reminds us of something similar. It's the fastest speed possible, and yet it's not infinite. It takes 8 minutes for light to reach Earth from the Sun. It takes over 4 years for it to reach us from the nearest star system. The light we see from distant galaxies left them billions of years ago. The universe doesn't rush, and in that delay, we get history, perspective, meaning. Each photon that arrives has been travelling patiently. Not stalled, not slow, but consistent, relentless. And in that patience, it tells us something we couldn't know any other way. So maybe progress isn't about beating the clock. Maybe it's about choosing what's worth our time. Even in human thought, the fastest ideas aren't always the best ones. Insight takes time. Synthesis takes time. A deeper understanding often comes not in a flash, but in a pause, in sitting with a problem long enough to notice what you missed the first time. We live in a world that moves quickly, but the universe doesn't mind waiting. Maybe the reason so much feels fast isn't because everything else is speeding up, but because we're the ones who are slow. Our eyes catch only a narrow band of light. Our ears hear just a slice of vibration. Our thoughts take time to form, speak, revise. We live inside a biological rhythm, one that runs on heartbeats, breath, the turn of the earth. But the universe moves on a different scale. There are particles that flicker into existence and vanish again in less than a trillionth of a second. There are processes so fast, so brief, they don't even register unless we build machines that can keep up. When atoms swap electrons, or photons strike a sensor, or quantum states shift in a fraction of a blink, it's not that the world is rushing. It's just that we're watching from far behind. Even when we observe something as basic as a chemical reaction, what we're seeing is already old. The event has happened. The bonds have changed. The light has travelled. And only then does the signal reach our instruments, and finally us. In that delay, meaning begins to form. But the event itself is long past. So when we talk about speed in the universe, what we often mean is speed compared to us, to our senses, to our tools, to the limits of our response time. From the perspective of a photon, travelling at light speed, there's no passage of time at all. In its own frame, strange as that is to imagine, the moment of departure and the moment of arrival are the same. No ticking clock, no sense of distance, just origin and destination collapsed into one. We, on the other hand, experience every step. We need time to move, to react, to process, to feel. So when we call something fast, maybe what we're really noticing is the contrast between its rhythm and ours. This applies not just to particles, but to events on every scale. A supernova, the collapse of a massive star, can happen in seconds. A black hole merger sends out gravitational waves that ripple for a heartbeat, then fade. These are cosmic events, immense and powerful, but they happen too quickly for us to experience directly. We catch them after the fact, with antennas, with sensors, with algorithms. We slow them down, stretch them out, translate them into forms we can absorb. Sound, image, language. But the original event moved too fast, and that's not a flaw in the universe. It's a reminder of where we stand within it. We're tuned to a middle world, not as quick as the quantum, not as patient as the planetary. We're slow, relatively speaking, but steady. And in that steadiness we build perspective, because speed in itself doesn't bring comprehension. Something can flash by so quickly that it leaves no impression. A data spike, a momentary burst. But without the time to reflect, there's no meaning, just motion. We slow things down, in physics, in memory, in conversation, so we can understand them. It's why we record things, why we rewind, why we explain, why we tell stories in sequence. It's not because the story happens that way. It's because we need it to happen that way. Even in science, most of what we know comes not from high-speed events, but from slow accumulation, long observations, careful adjustments, questions repeated, results refined, that patience is part of the process. Because the universe may not wait for us, but understanding does. Sometimes we're tempted to think of ourselves as advanced, because we can track particles, beam messages, accelerate ions to nearly the speed of light. But even at our fastest, we're still playing catch-up. Our computers are fast, but only in human terms. Our telescopes are precise, but only by our standards. The signals we detect from distant stars and galaxies took billions of years to reach us. They've been on their way since before Earth had oceans, and now they finally arrive, not to be greeted by something equally fast, but by being slow enough to pause and ask, what is this? That slowness is part of the gift, because it gives us time to notice, time to turn a stream of data into a pattern, and a pattern into an idea, time to make connections, to ask whether speed is always the goal, or whether sometimes the point is to stop and listen. So maybe we are slow, but maybe that slowness is exactly what lets us understand the fast things when they pass. Not in real time, but in reflection. We are not particles, we're not photons or waves. We're not the flash of a gamma burst or the swirl of a pulsar's beam. We're something else, slow, sensing creatures in a fast, quiet universe. And in that contrast, we begin to make sense of things. When we measure distance in space, we don't use kilometers or miles. Those numbers grow too quickly. The scales are too large. Instead, we talk in light years. The distance light travels in 1 year, moving at its maximum speed through empty space. 1 light year is nearly 10 trillion kilometers, and yet we toss the term around like it's casual, familiar. We say a star is 5 light years away, or a galaxy is millions of light years distant. And in doing so, we quietly combine two things that usually sit apart: space and time. Because a light year isn't just a measure of distance, it's also a measure of when. When we look at a star 1,000 light years away, we're not seeing it as it is. We're seeing it as it was 1,000 years ago. The light left before we were born, before modern history, before most of what we remember ever happened. That light has been moving toward us all this time, unstopped, unchanging. Only now, after centuries of travel, does it reach us, and when it does, we call it now. So we live in a kind of constant delay, not a failure of perception, just a feature of physics. The farther we look, the further back in time we see. In a way, the night sky's a time machine, a window into events that no longer exist in their original form, and every glint of starlight is a story still on its way to us. It's this fusion of space and time that gives light years their meaning, not just how far, but how long, and that blend becomes especially strange when you think about thought. Because thought, unlike light, can jump. You can think of a star 1 billion light years away in a single moment. You can imagine a galaxy spinning at the edge of the visible universe and hold it next to an image of your own street. There's no delay, no travel, just awareness. So in that way, we dream in light years. We close our eyes and move across the cosmos instantly. We imagine worlds we've never seen, or maybe can't ever see. Planets circling suns we'll never reach, civilizations we can't confirm, black holes spinning in dark regions of space, all of it accessible in thought. That's not physics, it's not motion. But it tells us something about the strange relationship between speed, distance, and mind. Because even though we're slow, our bodies, our senses, our tools, we can still conceive of fast things. We can hold vastness. We can picture galaxies colliding, or the structure of the universe at large, and do it all in the quiet of a single moment. Light needs years to make that journey, but we don't. We're not beating physics. We're just working in a different dimension, the one inside our awareness. And even though it doesn't change what's actually happening out there, it gives us a way to engage with it. Dreaming in light years doesn't move matter, but it moves meaning. It lets us tie ourselves to things that are otherwise beyond reach, And through that we build understanding, slow, deliberate, but rooted in something real. Because those stars we imagine, they're out there. That light, it's on its way. The data, it's arriving, piece by piece, photon by photon, and what we dream we sometimes find. Even now we're building telescopes that will look deeper into the past than ever before. Instruments sensitive enough to detect light from the first galaxies that formed over 13 billion years ago. That light has been moving since long before Earth formed oceans, and now it's almost here. Not because we're fast, but because we're patient. So even as we drift through time, we can picture ourselves among the stars, not as travellers, but as witnesses. As participants in a universe that moves too quickly for us to follow, but still leaves a trail of light we can slowly decode. And in our own way, we move too. Not in speed, but in understanding. A thought crosses a light year instantly, not because it arrives, but because it imagines. And in that moment, we're not bound by time. Still, the light continues to travel. Still, the universe unfolds at its own pace. And somewhere out there, a new photon begins its journey. Quiet, steady, a message with no hurry. There's a kind of patience in the way light moves. It doesn't hurry, it doesn't stop, it doesn't waver or drift off course. Once it begins its journey, it keeps going, straight ahead, without hesitation, through space, through time, through everything that might scatter or delay it. It carries on, unchanged in speed, unchanged in purpose. Even across billions of years, it doesn't forget where it was going. We often imagine ourselves as the ones doing the looking, scanning the sky, building instruments, gathering signals from the edges of the visible universe. But in a way, we're also being found, not by an intelligence or a message meant for us, but by something simpler, a presence, a trace. Light that's been travelling all this time, and now, after its long journey, it meets us here. You could say we're catching up to each other, the stars that emitted their light before humans ever existed, before our planet formed even, released those photons into the unknown. They didn't know what lay ahead. They didn't know they'd be intercepted, turned into data, into colour, into meaning. But here we are, receiving them, turning them into understanding. It's easy to forget that most of the light that reaches us has been travelling longer than we've been around to see it, and yet it arrives right on time. Not because it's aimed or timed or scheduled, but because we're finally in position to receive it, like two lines that began far apart and slowly converged. One a ray of light, the other a point of awareness. We think of light as fast, and it is. But when you look at the scale of the cosmos, it's also incredibly slow. It takes over 8 minutes just to reach us from the sun, hours from the outer planets, years from nearby stars, ages from distant galaxies. That light isn't rushing, it's just constant. It moves steadily through the void, passing whatever it passes, touching nothing unless something is there to meet it. And most of it won't be met. Most of it passes through empty space, through dust, through silence, through distances so large they can't be crossed in a human lifetime, or many. But when a planet does form, and when life does appear, and when eyes open to the sky, something changes. The light still travels the same, but now it's noticed. Now it lands on something that can receive it, not just absorb it, but wonder about it. Ask what it means, what it came from, what it shows. In that sense, the light that reaches us isn't just a signal, it's a reunion. Not because it missed us, but because we weren't here the last time it passed by. And that changes how we think about time. We imagine that we're discovering the universe as it is, but much of what we observe is how it was. The light we see tonight might have left its source before our species had language, or fire, or questions. And yet, here we are, ready to ask. So maybe it's not just that we see the light. Maybe the light sees us in the only way light can, by arriving. There's no intention, no awareness on its part, just the perfect alignment of movement and readiness. Something moving steadily through space, something else, at long last, ready to understand it. This is part of what gives astronomy its particular quiet feeling. It's calm. It's not just the vastness or the beauty. It's the realization that most of what we observe has been heading toward us for longer than we've existed. That the act of seeing something far away is also the act of stepping into a moment that's been approaching for eons. And even when we don't see it directly, even when the light is too faint or stretched or scattered, it's still part of the background. The faint glow of ancient radiation, the imprints left in structure and movement, the after effects of photons that passed long ago and bent the space around them just enough for us to notice. Light doesn't need to wait, but in a way, it does. It moves forward without knowing what's ahead. It keeps going. And when something is finally in place to receive it, a detector, a telescope, a retina, a mind, it's there, present, still carrying the imprint of where it came from. And maybe that's enough. It doesn't need to be fast, it doesn't need to be recent, it doesn't even need to be bright, it just needs to arrive, and we need to notice. So as we continue to watch the sky, to scan, to wonder, to interpret, we're not just looking outward, we're meeting light that's already on its way. We're catching signals that have been passing through the void for longer than we can grasp, and with each one, we become a little more aligned with the vastness we live in, not by travelling there, not by speeding up, just by being ready to receive. And that brings us to something else. If light can wait and we can meet it, then maybe the universe isn't in a hurry at all. Maybe we don't have to be either. We talk about beginnings, about expansion, about motion and speed and the limits that define them, and yet across all the movement, all the flickers of distance and time, the universe itself never seems to rush. It changes, it evolves, but not in a way that suggests urgency. Stars burn for billions of years, galaxies drift slowly apart, black holes form, merge, decay, not quickly, not with fanfare, but with the long patience of processes we can barely simulate, much less witness fully. Even when things happen suddenly by cosmic standards, they unfold across spans longer than the entire history of human civilization. Time out here is vast, not just in quantity, but in tone. There's a stillness within it. The universe is not lazy, it is not passive, it moves constantly, it expands, it loops and turns and folds, but nothing about it seems rushed. There's no scramble, no finish line. We're the ones who bring that. We rush, because our lives are brief, our memories short, our time as we understand it always feels like it's slipping away, so we try to move fast, to get ahead, to capture meaning quickly before the window closes, but space doesn't work that way. It opens steadily, it gives us signals slowly. The photons that reach us from far away took their time, not because they were slow, but because there was no faster way to arrive. The structure of reality doesn't care about speed the way we do. It cares about consistency, about connection, about balance. A single orbit of a distant planet around its star might take hundreds of Earth years, but that orbit is no less real, no less meaningful, just because we won't live to see it complete. A cloud of gas collapsing into a new star might take millions of years, but the process moves forward just the same, methodically, inevitably. Even entropy, that quiet engine of all things moving toward disorder, does its work at its own pace. Gradual, relentless, never rushed. And maybe that's what makes the universe what it is. Not just that it exists, but that it takes its time, that it doesn't need to finish, that there's no end point it's racing toward. We, on the other hand, often feel like we're trying to catch up. not just to knowledge or to light, but to meaning. We try to assemble what the universe is telling us faster than the signals arrive. But the more we watch, the more we listen, the more we learn that understanding takes time. It's not something we can force. Even the best ideas in science, the ones that shift how we see the world, arrive slowly. They gather from small observations. They repeat. They adjust. They wait to be tested. The quiet pace of the universe doesn't mean it has nothing to say. It means we have to meet it on its terms, with patience, with openness, with the willingness to let the message arrive when it's ready. And often, the most lasting insights come not from the moments we rush, but from the ones we linger in. A telescope left to stare at one patch of sky for weeks. A signal traced again and again until its meaning becomes clear. A question carried for years before the right experiment makes it testable. None of that is fast, but it moves us forward all the same. Maybe speed isn't what brings us closer to the truth. Maybe stillness is. Stillness in the way we look, in the way we wait, in the way we accept that some answers take more than a moment to form. After all, the universe is not in a hurry, and it's still here, still unfolding, still filled with light that hasn't yet arrived, with events we haven't yet witnessed, with signals still in flight, across years, across distance, across the quiet architecture of space and time. We don't need to chase them. We just need to be ready when they come. So wherever you are now, listening, drifting, thinking, thank you for spending this time here. If you found this gentle or grounding or just interesting enough to fall asleep to, you know what to do. Like subscribe, share it with a friend. But more than that, stay curious. Let your questions stretch a little longer. Let the answers come a little slower. And above all, take your time, because out here that's exactly what the universe is doing, and it's doing just fine. And with that, we'll let the questions rest for a while. There's always more to explore, more ideas just beyond the edge of thought, more light still on its way. But for now, it's enough to be here, to have listened, to have wondered. If you're still awake, thank you for dreaming with me, and if sleep has found you somewhere along the way, that's okay too. That's kind of the point. This is science for sleep, where the universe slows down just enough to carry you gently through it. Till next time, wherever you are, whenever you listen, good night.